Okay, we're going to do a whole bunch of practice here with exponentials, logs, and then logarithmic differentiation. Okay, so let's look at this guy. F of x is e raised to the cosine of x squared. I want to point out to you that is not e to the cosine squared of x. Those mean different things. Like maybe for fun, we'll do that one next. That would give us a different answer. Remember, this means you're taking the cosine, then squaring that answer. This is you're squaring your x first, then taking the cosine of that. Those mean different things. Okay, so let's take his derivative. The derivative of e to the anything is e to the same thing times the derivative of whatever is up top. Derivative of cosine of anything is negative sine of that same thing times the derivative, that's a parenthesis there, times the derivative of whatever is inside. In this case, derivative x squared is 2x. This guy is completely different. Let's do him. Also known here as dy dx. Derivative of e to the anything is e to the same thing times the derivative of whatever is up top. The derivative of cosine squared, we got to think of that guy as cosine squared. His derivative is bring the 2 down, leave the inside alone, drop that exponent down by 1, times the derivative of the inside. In this case, derivative of cosine is negative sine. Say we get completely different answers. Okay, what about this guy? We've got y equals 3 raised to some function. We cannot use power rule if our exponent is not just a constant number. If our exponent has x's or t's or whatever in it, you can't use power rule. The derivative, so just recall here, the derivative of b raised to some function is b raised to that same function times the natural log of b times the derivative of whatever is up top. So this guy's derivative, 3 raised to a power that has x in it. His derivative is 3 to the same thing. Leave the exponent alone. You pick up a natural log of 3. If that were e, natural log of e is just 1. You don't get this extra factor, or that extra factor is just 1 when that's e, times the derivative of whatever's up top, 2x plus 5. So we're done. That's our derivative. Sometimes students get confused with chain rule and they don't know when to stop. Sometimes they're like, well, I've still got a function. What's his derivative? No, this was my insidest function here. Once I write his derivative down, I'm done. You don't just keep going until you get to 1. Okay, I've got y of t is log of cosine of t squared. Then his derivative, which we might also call dy dt. Derivative of natural log of anything is 1 over that thing times the derivative of what's inside. Derivative of cosine of anything is negative sine of that same thing times the derivative of what's inside. Derivative of t squared with respect to t is 2t. So this might be better if we wrote this as maybe negative 2t sine of t squared over cosine of t squared. And like we could, if we wanted to, sine over cosine is just tangent. So you may have noticed here Like, let's look at this guy. Let's say y equals natural log of sine. Then his derivative would be 1 over sine times the derivative of the inside. Derivative of sine is cosine. Well, that's just cosine over sine. That's just cotangent. So we pick up different trig functions. Derivatives of logs of trig functions are often other trig functions, which is cool. That's going to come in really useful later, much further down the road when we're doing integration and we're doing U substitution. So we'll be able to prove later that the antiderivative of cotangent of t is natural log of sine of t plus some constant. Okay, let's look at another one. So I've got y equals log base 3. So I don't have natural log here. I treat him just like I would natural log, though. Derivative of log base anything of junk is 1 over that junk in parentheses. The key here is get all your parentheses. But you pick up an extra ln of 3 because of my base 3 times the derivative of the inside. Derivative of 5t squared plus 4 would be 10t. So this would look better if we rewrote like that. Okay, I like this problem a lot. I really like this problem. This one's neat. I've got x raised to the x power. Now, you might think, oh, I'll just do this. Bring the exponent down so that x came down to ground level and then drops down by 1. If you're thinking power rule, the first kind of derivative we learned to do. Nope, that's totally wrong. Wrong. You have to use logarithmic differentiation. If you have a variable up in your exponent, then you take the log of both sides. Log's a one-to-one function. I'm allowed to do that. The whole point of taking log is to bring this guy to ground level. No calculus has happened yet. That's just algebra. Now I take the derivative of both sides. With respect to x. Derivative of natural log of y is 1 over y times y prime. That's implicit differentiation there. On the other side, derivative, oh, look, I've got a product. One function, two functions. And you product rule. Derivative of the first times the second. Let me make my L's look more L-y and not 1. That's a 1 times natural log of x plus derivative of the second times leave the first alone. So that's just ln of x plus 1. Get some canceling there. So now just bringing everything up, I have y prime over y equals ln of x plus 1. I want to solve for y prime. So y prime will be the original y times this stuff. But I know what y is. It's x to the x. And then just for completeness here, I'm going to, we could stop there. I'm going to go ahead and distribute and say the derivative of x to the x is x to the x ln of x plus x to the x. Like without logarithmic differentiation, you never would have come up with that. Okay, here's one. We don't need to do logarithmic differentiation on it. It's just a bunch of product rules and power rules. It would take a while, though, because I've got 3 functions. I would have to do Derivative of the first times the whole thing. Call this the second. Plus derivative of the second. But to do the second, I've got a product. I would have to do a product rule again in the middle. And there's chain rule all over the place. We could do it, though. It's not that bad. Or I can use logarithmic differentiation to simplify that process. Take the natural log of everything, both sides. I get natural log of y equals ln of all that stuff. I'm going to actually write it all down. Let's write it down correctly, though. Now I'm going to use rules of logs. Multiplied inside becomes added outside. And I'm going to go ahead and I'm going to do two steps at once here. I hope you can follow my algebra. Multiplied inside becomes added outside. All these exponents are also going to come down to ground level. So I'm going to end up with this. If you can't see where I got all this from, you probably need to practice your rules of logs more. So all these multiplieds became pluses outside. I'm not inside a log anymore. And all these exponents came down to ground level. No calculus happened yet. That's just algebra. Now I take the derivative with respect to x of both sides. Derivative of natural log of y is 1 over y times y prime. And now these are all easy to take the derivative of. 4 comes along for the ride. Derivative of ln of x plus 3 is 1 over x plus 3 times the derivative of the inside, but derivative of all this stuff is just 1. 9 comes along for the ride. 3x plus 1 comes down to the bottom times the derivative here, which is just 3. 7 comes along for the ride. This guy is going to go into the bottom times the derivative of the inside. So I pick up a 2x here. It's smaller. Like we're pretty much done. We go a little smaller so that'll fit on that sheet. Okay, and now we just write down the answer that y is going to get multiplied over. So y prime will be the original times all that stuff. So I have to actually go back up and look. So it's a lot of writing to write down the answer. Oh, I just made stuff up there. That was a 3 and a 4. 3x minus 1 to the 9th. And x squared minus 5 to the 7th. So that's y. I'm multiplying all of this times y. And then what do we get there? 27 over 3x minus 1. And then 14x over x squared minus 5. So it's not a pretty answer, but I'm telling you, that was so much easier than doing product rule twice and chain rule 3 times. This one's going to be similar. I could do quotient rule, and then when I get to the very first step, derivative of the top, I would have to do product rule, and I'd have to use quotient rule twice or chain rule twice in there. I don't want to. I'm going to take the log of both sides. So all that stuff being there. But that will be, anybody on top is going to be positive. Anybody on the bottom is negative. All the exponents come down to ground level. Remember, these are all logs. So these guys were on top. That's why they're both positive. He was on the bottom. That's why he's negative. All the exponents came down. Take the derivative of both sides. Derivative of natural log of y is 1 over y times y prime. Here we get 4 over x plus 5. Derivative of x plus 5 is just 1. 3 over x minus 2. Derivative of x minus 2 is just 1. Minus 8 over x plus 7. Derivative of x plus 7 is just 1. I don't need any of those. So y prime equals y times all this stuff. And y is up there somewhere. You don't need to see me rewrite all that out. Okay, what if we had something like this? Now I've got a function of t raised to a different function of t. Now I have to use logarithmic differentiation. On those last couple, it was just helpful. It just made it a little prettier. Now it's required. So let's rename this guy y. And that guy is raised to the tangent of t. So we apply the function natural log to both sides. And I'll write out all the steps here. The whole reason we take logs is to use the rules of logs. This tangent of t will come down to ground level. Now I take the derivative with respect to t, that's my independent variable, of both sides. Derivative of natural log of y is 1 over y times y prime. Derivative here, I've got two functions. I have to use product rule. Derivative of tangent is secant squared of my input, times leaves the second guy alone, plus derivative of log of anything is 1 over that thing, times the derivative of whatever was inside. Derivative of t squared plus 1 is just 2t, times the first guy. This is product rule. And now, like the math, the hard part's all done. All the calculus is done. Just multiply that y back over. Y prime will be y, which was t squared plus 1 raised to the tangent of t times all this stuff. And I'll clean up anything that obviously cleans up, but there's not much. Like I can put all this on top of this fraction. And we're done. Like that's not, nothing you're going to do is going to clean that up anymore. Okay, that's a good place to stop there.